This video is on trig substitution. Now, with regular substitution, and usually we call this u substitution, you guys choose some function for u that you then substitute back into the integral, and you sort of change all of your x's, say, to u's, and the integral becomes then integrable. And we're going to do the exact same idea with this, except for this time we're going to be using trig functions for the substitution with our functions. So here's an example. Let's find the integral of the square root of 9 minus x squared all over x squared dx. Now, I'm going to, on this one, sort of give you the substitution, then explain why that is the substitution. So we are going to substitute that x, we're going to substitute in for x 3 times the sine of theta. Now I'm going to show you two different ways to sort of look at why this substitution is going to work. And the key here is that it's going to get rid of that square root that's in our integral. That square root is causing a lot of issues. So one of the kind of ways that you can look at this to get rid of the square root is we could substitute this x. We could take that x and just substitute it back into this equation, which we're going to have to do at some point anyways. But for right now, I'm only going to look at that square root. That's the issue. So if I take that x and plug it back into the square root, I would have, I'm going to write this kind of somewhere where it's not all that necessary. How about over here? So we would have the square root of 9 minus, now x is 3 times the sine of theta, square that, because x is squared. Now notice that 3 squared is 9, so I could factor out a 9. That would leave me with 1 minus sine squared of theta. The square root of 9 is 3, so I'm going to bring that outside of the square root. And 1 minus sine squared is cosine squared. I'm using a trig identity here, that cosine squared plus sine squared is 1, and so then if I subtract sine squared over to the other side and solve for cosine squared, I would get 1 minus sine squared is cosine squared. So now I have a square and a square root, which sort of cancel each other for lack of a better word, and I'm left with 3 times the cosine of theta. So notice that that square root of 9 minus x squared is equal to 3 times the cosine of theta. Square root is out of there. So that's one way to look at this. The way that I prefer on these is that I usually draw a triangle. Now I'm going to draw a triangle with theta as my angle right there. And I know that if I make this substitution of x equals 3 times the sine of theta, that the sine of theta is equal to x over 3. Sine is opposite over hypotenuse, so that would be opposite would be x, hypotenuse would be 3. And now if I want to fill in this other leg, so I'm now going to find this other leg just looking at the triangle. So I'm not looking at any other information on this page, just the triangle. This leg would have to be the hypotenuse squared minus that leg of x squared. Notice that that is that square root of 9 minus x squared, and that matches what we have in our integral. So when I do these problems and I choose my x value here, I'm choosing that x so that this triangle gets the correct square root back to the integral. I'm going to say that again. The x that I choose goes with this triangle, and whatever square root comes out of the triangle better match the square root that I have in my integral. That way I know I have chosen a correct value of x. Okay, so that's sort of the tricky part on getting started. What to even choose for x? So again, I use the triangle. Now it's a matter of substituting everything in. We've got x's we've got to substitute in, and we also have this dx, and he's easy to forget about. But he's in there, and we've got to substitute in for that as well. All right, so here we go with the substitutions. Well, we need a dx. We don't have that written down here anywhere, so let's find it. Dx, that is going to be the derivative of what I chose for x, which would be 3 times cosine of theta. All right, so now for some substitutions. So this now is going to become the integral of, now this square root of 9 minus x squared, that, remember we got 3 times cosine of theta. If you want to get it from this triangle, what I do is I look at the triangle and I know that I want this square root and I want a number. So that is the adjacent and a number. Adjacent and hypotenuse is what I meant to say. Adjacent and hypotenuse has to do with cosine. So I know that from this triangle, the cosine of theta is equal to the square root of 9 minus x squared over 3. And so that gives me that square root of 9 minus x squared is 3 cosine theta. I got the same thing I did here, just in a little bit of a different way, just looking at the triangle. But I do this all from the triangle. All right, so now that we have that the square root of 9 minus x squared is 3 cosine theta, let's substitute it in. So square root is 3 cosine of theta, and dx was 3 cosine theta, so let's put that in there. That's going to be in the numerator. And then in the denominator, I have this x squared. So I've got 3, and I'm going to square that, and sine, and square that. X was 3 sine of theta, so I'm going to square it, put it in the denominator. And I guess here's another little detail that I just left out. The derivative does include a d theta right there, and so the d theta really comes from that derivative of x. Okay, so notice now that I've changed my x's to thetas. So now I have a new problem. This is an entirely different integral. So now I've got the integral of, let's see, those 3's all cancel out, and I've got cosine squared divided by sine squared. Because the cosine is squared in the numerator, now I'm looking at this as a completely different integral. Because it's squared, I can't do a u substitution with it. I've got to try something else. Let's see here. Cosine over sine is cotangent. And that doesn't help me because cotangent squared is not a derivative of any trig functions, but cosecant squared is. And if I use a trig identity, cotangent squared is cosecant squared minus 1. This, I do know the antiderivative of cosecant squared is negative cotangent. And the integral of 1 with respect to theta right now, careful here, our integral is with respect to theta that we're looking at right now. So that's a theta, so minus theta. All right, now here's where most people are tempted to stop. We've done an integral, but we're not quite done yet. And the reason we're not done is because the original integral had x's in it. So we really have to transform this back to x's. And the reason that I like this triangle so much is the triangle has x's and theta, and so I can use it to take this theta and convert it back to something with x's in it. So let's see, cotangent is sort of the opposite of tangent. Tangent is opposite over adjacent, so cotangent is going to be adjacent over opposite. So I'm going to transfer this back. I still have a negative sign in there. And it's going to be adjacent, which is that square root of 9 minus x squared, over opposite, so over x. Now theta is a little bit tricky. We can't get it from the triangle. Where I'm going to get it from is, actually this is a better thing to look at right here. X over 3 is equal to the sine of theta. So if I take the arc sine of x over 3, that would give me theta. So theta is the inverse sine of x over 3. And what I was looking for is something that theta was equal to that, that had x's in it. Now notice I could have written this with an inverse cosine. There are other options. Hopefully that didn't confuse you too much, but there are multiple answers to this problem at times. All right, so now I'm back to x's. Now I can add my c and be done. Okay, so kind of backing up on this whole process. If we have an integral here, now notice that this was not possible by U substitution, and notice that it has the square root in it. That square root is really key and a lot of times works out well with Trig Sub. You're going to choose a trig function that goes along with a triangle so that the square root matches the square root that is in the integral. From there, substitute in dx, substitute in the square root, substitute in x's. Then look at your new integral. Now this new integral, it could be just some sort of a trick with trig, like we'd had. It's possible that you could have a U substitution after this. Or it's possible that it's then an integration by parts. You kind of have a whole bag of tricks with integrals, and you may need to pull those out on this next integral. This trig sub is always an integral within an integral, and then you always have to back it back up to the x's here, and I use the triangle. All right, so that's the process. Now a couple kind of tricks here. So a couple tricks depending on which type of square root you're given. So in general with these problems, now this is not always true, but in general, a lot of times we have, square root of, say, some number squared minus x squared, like the last problem we have. Another one we could have like the square root of some number squared plus x squared. And in other problems, we've got square root of x squared minus a number squared. So these are kind of not all the possibilities, but in general, these are the ones that come up the most. So if you notice on our last problem with this one, we used the substitution that x was equal to a, in this case our a was 3 on the last problem, sine of theta. And the reason that that worked is because then the sine of theta was equal to x over a, and we could draw a triangle from there with theta in the angle, and sine is opposite over hypotenuse. Opposite is x over hypotenuse of a. Then the other leg, if we solve for it using Pythagorean Theorem, then it would be the hypotenuse squared minus x squared. And just notice that that root matches the root we started with. Now for this a squared plus x squared, that one, a good choice for a substitution, a lot of the times will be a times tangent of theta. I'm going to do the same thing here where I'll show you how the triangle works to get us that square root. So the tangent of theta is equal to x over a. And if I draw the triangle, tangent is opposite over adjacent. And Pythagorean Theorem says that the hypotenuse is then a squared plus x squared. Just again, notice the square root matches up. And this last one, a lot of times a good choice can be x equals a secant of theta. And for that one, the secant of theta is then equal to x over a. So triangle, if I put theta in there, secant is going to be the hypotenuse over the adjacent leg. And so then the other leg of the triangle, I would have square root of the hypotenuse squared, so x squared minus a squared. There we go. So on all of these choices for x are in general good choices. They sometimes don't work, and there are oftentimes other choices that still can work with that square root. This is not like you do not need to choose these x's every time. I'm just giving you a guideline for some good choices for them. Also, I think it's much better to use your intuition, with the triangle, and you need Pythagorean Theorem and some trig identities, like that cosine squared plus sine squared is 1. With those two facts, you can sort out what would be a good substitution to get rid of that square root, with some fiddling involved. So I don't necessarily want you to memorize these choices for x's. But I just wanted to give them to you as a good starting point with all of this. All right, I think that's all I've got for you for now.